it's noon and we can start. So we're very happy to have Adam Kaufman here. Well, Adam Kaufman in Boulder and visiting us virtually today. So Adam is an associate fellow at JILA and CU Boulder. He did his undergraduate degree at Amherst College and his PhD at CU Boulder in the group of Cindy Regal. And in particular, his PhD work, he was doing really pioneering experiments controlling the quantum states of individual atoms in optical tweezers, bringing them together and entangling them. And for that work, he was awarded the APS's DAMOP Thesis Award for the best thesis in AMO physics nationwide. And then he went on to do a postdoc at Harvard, doing some beautiful experiments using a quantum gas microscope to study topics like thermalization in closed quantum systems and the connections to entanglement there. And since 2017, he's been at JILA, and he's also on the adjunct faculty at CU Boulder. And he will be telling us today about the beautiful work he's been doing there on atom arrays of ultra-cold strontium. Before I hand it over to Adam, I'll just sort of say something about the logistics of this virtual seminar for those of you who haven't done this before. So hopefully you know there's a chat feature in Zoom. If you want to ask a question, maybe you think of a question even along the way or towards the end. At any point, you can enter questions into the chat. And Adam will probably pause partway through to take questions, and then we'll certainly also take questions at the end, and I'll be helping moderate that. So with that, I'll hand it over to Adam to give our seminar.
All right. Thanks so much for the invitation to speak here, albeit virtually. I look forward to, in the future, being able to visit all the great labs there. Yeah, so with that, I'll jump right into it. So I'll be telling you about recent work coming out of my lab over the past 3 years at JILA, specifically focusing on atom arrays of strontium. Maybe I should just check. You can hear me just fine, okay, Monica?
Yes.
Very good. All right. Okay, so and specifically, I'll be focusing on recent experiments that we've been doing in metrology, although this experiment has sort of broad goals for it. Okay, so a key focus of my work really over the course of my career has been learning ways of microscopically controlling quantum systems. And this basic focus is, of course, integral to quantum science as a whole. So it's used for quantum communication if I want to transmit information between distant qubits. It's a key strength for being able to characterize new states of matter in quantum simulation platforms. And it's quite fundamental to quantum computing, where to be able to perform generic computations, you really need to be able to control individual qubits. One focus in recent years as our ability to control these systems has really improved, has been to figure out how to combine scalability, that is the ability to make a system larger and larger, with the degree of control we now have in few qubit systems. And this technical goal is something that my lab really focuses on. And what today I'll be talking about that's a bit maybe unique is that we're really applying this not necessarily to these goals on the right here, but really to the context of metrology. And I'll be talking about a new clock platform that we've been developing. So before I jump into our experiment in particular, I wanted to sort of give a flavor that's of why this kind of goal is so challenging. So why is it hard to combine, for instance, control and scalability? And there's sort of two perspectives on this. So one is, as I have more and more atoms, I need to individually control all of them. Say if I need a laser for every one of those atoms, then there's some form of classical noise that might be on my laser, for instance, just power fluctuations. And the more atoms I have, the more challenging it can become to control them all individually. Furthermore, there are effects of quantum noise, which is just the fact that I might have some pure quantum state to begin with, but it might couple to the environment and become a state which has entropy. So despite these challenges, there have been a number of really impressive experiments that have actually pushed us further in spite of the sort of grave challenges that we face in scaling a system while retaining control. So for instance, we have many body experiments coming out of Marcus Greiner's group where they were able to see any ferromagnetism in a Fermi-Hubbard model. There are the recent experiments coming out of the Google experiment where they could observe so-called quantum supremacy in a large qubit array of superconducting qubits. And also there have been a number of experiments in trapped ions and also Rydberg atom arrays that I would sort of put in the category of designer quantum systems, where we can individually control and tailor the quantum mechanics that we want to look at in larger and larger systems. So that's the sort of control side of things. And I would separate that from the detection side, where I think in many ways there are parts of this problem that we've really figured out, in the sense that we can have large arrays of neutral atoms or superconducting qubits or trapped ions, and we can individually image all of them at pretty high fidelity. But another challenge that's talked about a little bit less that I just wanted to highlight here is the problem of as we use these single particle observables that we have in these experiments, often we want to measure things like correlators or entanglement. And to do that, we often need to run our experiment many, many times. So I'm just showing you several different experiments here. These ones on the left are with neutral atoms, and these ones on the right are with, this one on the right is with trapped ions. And they're running experiments that they have to get statistics, they have to run it thousands to 100,000 times. And the cycle times of these experiments can range from 1 minute to 50 milliseconds. You know, as you have to run your experiment more and more times, if you have a cycle time that's this long, that can make things quite challenging. And as I mentioned, one of the key things that we really want to do with these kinds of systems is measure observables that we otherwise might not have access to in, for instance, a solid state system. And to really get to these observables, we need to average down a lot. So what I'm going to be talking about today is really this experimental platform known as optical tweezers that really make a lot of headway at some of these problems by combining a new set of technical capabilities. So what I'm showing you here is a picture of a single atom in an optical tweezer. And an optical tweezer is just a tightly focused beam of light at which we can trap individual single neutral atoms. And this technique in general was really pioneered in the Grand GA group in the 2000s. As I sort of alluded to, what's so nice about this platform is it really combines simplicity with control. So it's not just that, it's really that they combine speed, control, scalability, new ways of making low entropy systems, and also a huge variety of interactions can be engineered into these systems. And I'm just flashing here a number of different groups that have been developing these systems. On the top here are neutral atoms, and in the bottom is a recent advent, which is the use of tweezers for actually molecules. And just to highlight some fancy pictures that have been coming out of the Brouwer's group in Paris, you can even make 3D arrays of neutral atoms and, you know, Eiffel Tower arrays if you're interested in going into quantum simulation of the Eiffel Tower. Okay, so this basic architecture has been used for a variety of applications, including quantum information processing, as well as what I might describe as few to many body physics, where on the left here, this was work that was done in Cindy Riegel's group in 2014, where they were looking at few body quantum optics experiments, and then all the way up to more recently, where in Misha Lukin's group and the collaboration at the CUA, they were able to make large scale entangled states of 20 particle systems. So the work that my lab has really been focusing on has been applying optical tweezer arrays to a new species of atoms known as alkaline-earth atoms. And before I dive into the physics that we've been working on and sort of highlight the many directions that this kind of approach enables, I just wanted to point out that I'm not the only one exploring this. There are actually a number of groups, including Manuel Andres' group and Jeff Thompson's group, and also a company, Atom Computing. And actually, in recent months, I've learned of at least 5 different experiments that are on the way in this particular field. So it's a really exciting time for this generic direction of tweezer arrays and alkaline-earth atoms. Okay, so what are alkaline-earth atoms and why do we care about them? So one example of an alkaline-earth atom, which is the one that we work with, is strontium. Strontium is a 2-electron atom, meaning it has 2 electrons in its valence shell. And this is contrasted with, say, alkali atoms, which have a single electron. And these guys are nice because they have a slew of transitions that can be very useful. So there's this blue transition, which I'll refer to, which we use for imaging, which is a very fast transition. There's a narrower transition, this cooling transition here. which is which is used for cooling. And then finally, there's this transition known as the clock transition, which is which is really something that makes this species quite famous. So these things can be used for, these different transitions can be used for a variety of different applications. So as I mentioned, this blue transition can be used for high resolution spatial imaging because the wavelength is so short and the scattering rate is fast, so you can collect photons quickly. This red transition can be used for high fidelity ground state cooling, and I'll talk about how we do this and what these kinds of plots on the right here mean. This clock transition, as I mentioned, can be used for optical frequency metrology. And finally, another thing that's nice about this species is that it has a nuclear degree of freedom that can be well controlled and isolated from the environment to make things like a nuclear qubit. So all of these different capabilities can be combined in interesting ways. So for instance, if you combine this nuclear qubit with this narrow transition, you can create new kinds of architectures for detecting and controlling individual qubits. There are a number of interesting papers proposing how this nuclear degree of freedom can give rise to interesting spin models, such as SUN models, and being able to detect those at a single particle level might lead to a new understanding of a number of many-body physics phenomena that actually arise in solids. There have been several proposals looking at how to make new 2-qubit gate architectures that rely on things like spin orbital exchange or Rydberg physics. And finally, and this is what will be really the focus of my talk today, one can combine these imaging, cooling, and clock capabilities to create a new clock architecture. So that really brings me to the core of my talk. So as an outline, I'll be describing just briefly our optical tweezer platform. Then I'll describe our first work looking at creating a tweezer-based clock. I'll finally discuss our very recent results where we've been able to really push this platform up to hundreds of atoms and tens of seconds coherence times up to actually 40 seconds. And then finally, I'll talk about an outlook for our experiment, what we're planning to do next. Okay, one other thing is that there's another goal for this project, which is really to get to low entropy Hubbard physics in a new way. I mean, I'm not actually going to have time to discuss that, but if there are questions, I can maybe address them. All right, I'm just going to take a sip of water here. Okay, so to briefly go over the core of our apparatus and what it looks like, on the left here is just a CAD model of what our system looks like. This black thing is our microscope objective. This thing here down is our cell. We have this Maycore structure here on which our objective sits so that we can register a number of different optical potentials to our microscope, including an optical lattice, which I'll make reference to later in the talk. And here's a picture here of a tweezer array that we could project into this cell. On the right here is an actual picture of our setup, and that blue thing in the center here is a picture of an actual magneto-optical trap of millikelvin temperature atoms. That's about 10 to the 7 atoms. Okay, to actually trap individual atoms, we need some way of making arrays, and my group does this in a number of different ways. So this is just this is probably as technical as this talk will get. The way we make our trap arrays is by using AODs, so these are acousto-optic deflectors, by driving them with custom electronics that we have for fast control of RF frequencies. And by putting multiple tones into these AODs, we can make multiple different traps when they're focused down to our objective. And here are just pictures of what these traps and arrays might look like. Very recently, I've had the pleasure of having a PhD student from Germany, Felix Röntgen, who's been working on implementing an SLM in our experiments. And now we can actually have more complicated arrays like this triangular setup or even a hexagonal lattice. And this is a very nice capability to have for really pushing the kinds of physics we can look at. And I just wanted to highlight it here. Okay, so once we overlap one of these arrays with that cold cloud that I was showing you a picture of earlier, we can trap individual atoms in those arrays. And this microscope that we use to make our traps, we really worked hard to get right and work with all of the optics in our setup. And when doing that, we can actually have a really small PSF for the atoms. This is a diffraction limited spot of about 420 nanometers. So this is really comparable to the kinds of optical properties that you'd have in a quantum gas microscope experiment. When the atoms are trapped and we shine both a combination of that blue cooling light and that red, blue imaging light and red cooling light, we can image the atoms at high fidelity. The exact fidelities that we get depend on the tweezer wavelength that we're using, and I'll allude to that later in the talk. But at best, we can get up to fidelities like I'm showing here. This peak on the left here corresponds to when we don't have an atom in our trap, and this peak on the right corresponds to when we do. And by being able to separate this bibonal distribution, we can at high fidelity distinguish when we have an atom. Okay, so the next important thing is that in our first early work, what we were using was these 515 nanometer green tweezers, which allowed us to address this cooling transition for very narrow spectroscopy for doing ground state cooling. I'm not going to say too much about this other than that using 3 sets of laser beams, we could address multiple motional axes of our trap and do ground state cooling. So these 2 spectra here are basically indicating that we have a high ground state fraction. So this peak on the right here in this picture here, for instance, corresponds to when we'd add a quantum of motion by doing sideband spectroscopy, and on the left here corresponds to when we remove a quantum of motion. When the atom is in the ground state, this transition on the left here doesn't exist, and hence this asymmetry allows us to quantify the ground state fraction. And in particular, for all 3 axes of the trap, we can get to around 80% 3D ground state fraction. Okay, so as of about 2018, we were able to have single strontium in traps with single particle detection, single particle isolation, tunable particle number, and good control of the atomic motion. I mean, we can do this, we can make them very cold. And then finally, we could do this at low dead time, meaning that the actual rep rate of our experiment was quite high. So I just wanted to highlight all those features because they're actually quite relevant for the clock physics that I'll talk about. Okay, maybe that's a good moment to just take a second. Are there any questions? I would have seen a chat bar. It looks up there.
So I see something in the chat. Can you see that, Adam, or should I?
I actually can't. The laser.
So there's a question.
Well, there's the mouse. So maybe if you should read it. Okay.
So Ben asks, how do you ensure that the tweezers at 515 nanometers and 813 nanometers are overlapped when using an SLM to generate arrays? I was going to ask that too. Good question.
So when I get to this part of the talk, I'll be able to address that. And just to be clear, for the data that I've been talking about so far, we haven't actually combined those yet, but we do in this part of the talk. So maybe I'll circle back to that point when I get there. Does that sound good? Maybe Monica can speak for then. Okay. All right. So I'll keep going there. Yeah. Sorry. Okay. All right. So, oh yeah. Sorry. What'd you say?
Oh, sorry. For everybody listening, I just want to say, feel free to put questions in the chat at any time, and then next time you pause, we'll ask you.
Okay. Cool. So for the next part of the talk, I'm really going to describe how we use these capabilities for a tweezer clock. So before I jump into that, I just want to describe, how an atomic clock works. So a clock in general works by referencing or measuring the passage of time based on some periodic behavior. So, this could be how many times a pendulum swings, and you can count those repetitions as a way of keeping track of the passage of time. If you're really desperate, you might use something like a sundial. In an atom, the situation is pretty similar in the sense that you can think of the regular motion as being the oscillations of the drive that might drive a transition in the atom. Alternatively, you can think of it as the rate at which a coherence evolves between a superposition of a ground and excited state. Or you can think of it as just the electron wave packet is oscillating back and forth when you induce a coherence between a ground state and an excited state. The lifetime of this superposition, or the length of time over which these oscillations in the electron wave packet persist, really dictates the quality factor of this oscillator. So in atomic clocks in general, their performance is really dictated by the stability of the clock, which is based on corresponds to the rate at which precision is accrued as a function of averaging time. And a key point is that this precision does better and better with the quality factor of the transition. And for atomic clocks, this can be either in a microwave transition, such as in the cesium clock, or an optical transition, such as the trapped ion or optical lattice clocks that I'll describe in a moment. And this transition frequency being 10 to the 5 higher is really why this architecture has become so powerful. Just to sort of home in on that point, this is a really nice plot that I like from this review paper that shows how the optical atomic clocks in the red have really caught up with the microwave clocks in the blue and pushed the fractional frequency uncertainty that these systems can achieve down into the sort of 10 to the minus 18 and even in precision 10 to the minus 19. This is actually the fractional frequency uncertainty in the systematics of the system. And so this can be used for a variety of applications, including gravitational redshifts, geodesy, navigation and timekeeping, time variations of fundamental constants, a lot of different things. And they're also just fundamentally interesting measurement systems. So the leading platforms for atomic clocks, optical atomic clocks these days has really been trapped ion systems, which operate with a single ion that's interrogated at a high duty cycle and can leverage quantum information architectures that have really been pioneered in trapped ion systems. As well as, and then another leading platform are optical lattice clocks, which use a large number of atoms, utilize optical trapping to hold on to them. But the duty cycle of these experiments, really meaning the speed at which you can, or the fraction of time that you spend interrogating the sample versus preparing or detecting the sample, can be more relevant than in, say, trapped ions, where everything can be super fast because the ion is held onto so tightly. So the question that my group has been asking is whether there's sort of room in between these two platforms for a new kind of architecture. So to really get at why I think, and we think that these tweezers can be useful for clocks, I want to get at sort of the key things that make an optical clock work well. So in an optical clock, you have some clock laser, that's sort of your flywheel that keeps track of the passage of time. And you lock it to some reference cavity, which takes care of a large range of bandwidth. But this cavity is, of course, some solid state thing that can move and vary as a function of time as a result of any kind of environmental perturbation. And so the atoms are used as a slow reference on this feedback that the cavity might experience. So this basic setup has two dominant things that one needs to consider. So one is just the stability, which depends on the number of atoms that you have, which says basically the shot noise the atom shot noise that you have per run of your experiment. And further, the precision or how much frequency information you gain per run of your experiment, and that depends on the quality factor. The other thing that matters is this effect known as the Dicke effect, which is talked about a little bit less, but is actually super important. It's the idea that this laser, although it's locked to some amazing cavity, this cavity has high frequency noise on it due to its thermal noise floor that gets written on the laser. And although you'd think that that might average out as you probe the laser's frequency with the atoms at some slow repetition, in fact, this gets aliased down into the time domain of your experiment and causes the stability to be much worse. So in optical lattice clocks, this can actually be a very important consideration. So to put these two criteria in the context of the leading platforms, for trapped ions, you have low atom number, whereas for optical lattice clocks, and there are two different architectures these days, the one-dimensional and three-dimensional versions, they perform better and better with increasing number, going from trapped ions to the optical lattice clocks. But going from lattice clocks to trapped ions, you have increasing duty cycle. So these two metrics that I was just describing actually are not, it's not like one platform optimizes on both of them. So just to really hone in on why we started thinking about the tweezer clock ideas in the context of both these strengths and also results that were occurring when we were starting up. So the Ludlow group had this incredible paper. This Ludlow group is at NIST, where because the Dicke effect was such a problem for the optical lattice clocks, to address it, they actually just duplicated the lattice clock so they could perform interleaved measurements on 2 samples of atoms. So this is really just saying that it's such a problem that the Dicke effect is very motivating for having brute force solutions to these issues. A second point that I wanted to make is that The Q really depends on how long you can interrogate the atoms for. And there was this amazing paper from the Yi group showing that if you could trap atoms not in a 1D lattice, but in a 3D lattice where there's actually a single atom per site, then you can have improved coherence times, which means that your Q is actually longer, is greater, and you can mitigate interaction shifts, which both can dephase the atom and also lead to systematics. So the tweezers sort of combine all these different points that I was just saying in a new way. So we have immediately single particle isolation, which means we should be able to get to long coherence times. We have tunable spacing of the traps, which I haven't explained why that's important yet, but I want to put up this point because I'll show later that it's actually quite relevant. And this system can be scalable to, say, 5 atoms, which is really what I'm going to be talking about in the middle of the talk here, up to, I'd argue, about 1,000 atoms. Furthermore, these systems can be operated at very high duty cycle, which is to say that because the atomic imaging can be very low loss, you can actually just recycle the same atoms and interrogate them over and over again. And I'll show you exactly how we can do that in our setup. So this suggests that we can combine both intermediate scale atom numbers with high duty cycle and get to long coherence times by having single particle isolation. So to get at doing this, we really relied early on this clock light network that exists in JILA, and I just wanted to be very explicit about the fact that we are quite fortunate to have this, and it's also quite cool the way it's set up. So there's this this amazing laser in the Yi group known as the clock laser. So it looks like this football thing, and it exists in this room that's called the sanctuary or something. And this laser has a line width of about 8 millihertz when it comes out of when it's locked, after it's locked to this cavity here, the football. So then this clock laser travels on a fiber to the Yi lab optical lattice clocks. From that lab, it travels on another fiber over to James Thomson's lab, where they have an amazing cavity system. And then from James Thomson's lab, it travels over to my lab. And then on each of these fibers, there is fiber noise cancellation to take 500 hertz to a kilohertz of frequency noise and bring it down to the sort of 100 to 50 millihertz range that we hope to get from this laser. And this is key for both the physics that I'll be talking about in my group, but also more generally for ideas in quantum information and also even making entangled clocks. Okay, so to really make use of this laser and also to get the best stability possible, we went through the numbers and realized that what would be key were a number of different things. So one, it became obvious in initial explorations that the coherence times and contrast that we could get in the experiment really depended on getting to ground state temperatures. The interferometric stability of the tweezer array was critical, which meant we needed to make sure that the tweezers were well referenced to the phase of the clock laser. And finally, we needed to make sure that we could hold on to the atoms for a long time. And this is sort of a technical point, but actually these AODs that we use to make the tweezers need to be optimized in a special way so that there's very minimal heating in the traps. The upshot of these, particularly the temperature point and the heating point, is that we needed to operate with very deep traps and further in a configuration that was inefficient with respect to power. And so this meant that we had to operate in this regime of having only about 10 tweezers. So to really diagnose the coherence times that we get, we did a Ramsey experiment, which is quite simply, I do a pi/2 pulse to park my atom on the in the x direction of the Bloch sphere. I look at phase evolution of my oscillator, of my atomic oscillator with respect to my laser, and then I do another pi/2 pulse to read out this phase. Because we were working with a small number of atoms, we have to repeat this on the order of 50 times. And I point this out now because later on, when we have many more atoms, we actually don't need to do this. So in this early result, we were able to see that we could have about 3 seconds of coherence time, which at the time was actually within a factor of 2 or 3 of the state of the art. And I wanted to highlight these guys here who really pushed on all the technical features here that were necessary to get to these coherence times. One of the things that was quite interesting about this work was that we initially were quite stumped by what was setting our coherence time. So I'm showing here a plot of the observed Ramsey contrast as a function of time for different depths of our traps. So for the shallowest traps, we had the longest coherence times, and then they got worse and worse as we went to deeper traps. And we weren't sure what was causing this. It's not totally surprising that the tweezer depth would cause a problem, but we couldn't figure out why. And then what we figured out was something quite interesting, which is that because the different frequencies of the tweezers, because the different tweezers are each at a different optical frequency, because when you make these different traps, the AODs actually shift the frequency of the tweezers, it means that all of the tweezers cannot simultaneously be at the magic wavelength. And that means that even for 5 megahertz, which is the frequency difference, out of hundreds of terahertz, which is the frequency of the tweezer laser, that results in a shift in the clock frequency that can actually matter. And actually this black line here is exactly our expectation of this effect. And this dashed gray line is the sum of that effect and spontaneous emission that we expect from our tweezer light. So it took us a bit to figure this out, but we were quite surprised that such a small fractional frequency difference would matter, but it turns out it does for these long interrogation times. And we can actually look at the phase evolution of individual sites and see that exactly this effect is occurring. So as you go from the right site down to the left site, you can see that the phase is occurring with a slightly different slope as a result of these shifts. Okay, so in addition to having long coherence times, we could also get to very high duty cycles. So what that means is we would load our traps and then cycle between imaging, cooling, and then clock interrogation, and then imaging. And that's what all of these things, these colors indicate here. And we can do this some number of times. So here, this is not a particularly great duty cycle that I'm showing, but when we go to longer interrogation times, we can actually have duty cycles that approach above 90%. And just to point out, these data set on the right here really correspond to 20 seconds of near continuous clock interrogation. And I'm sort of sweeping under the rug that during this actually took a lot of work to get this to be successful, because there are many different steps in the experiment that need to work very well on a short time scale. And in fact, the dead time in these experiments was only 90 milliseconds, which included ground state cooling, detection, repumping, and changing all the trap parameters for all of those different phases of the experiment, as well as also changing magnetic fields. So it took a lot of work to get that to succeed. So the upshot of all of this is that at that time, so this is about, this data was February or might have been March 2019, we can have frequency stabilities of 4.7 times 10 to the minus 16 per tau, which, to put in context, the state of the art as of 2019 was 4.7 times 10 to the minus 17. Excuse me, so that means we were within about a factor of 10. And what we estimated was that with 150 atoms and 2 seconds of interrogation, we could actually match this state-of-the-art number. And I want to point this out just because it's relevant to what follows in a moment. And further, I wanted to highlight the work of Manuel Andres' group, which also pushed to larger atom numbers, but at lower stabilities where they weren't necessarily working at as long interrogation times. So one thing I want to point out before I move on to our next, what we've been working on very recently, is that these low dead times could be useful for deployable atomic clocks, where you might not be working with as good a cavity, but if this cavity is moving around a lot, by having a low latency atomic feedback, that might help with such problems. Okay. All right, so I think I'm going a little bit slower than I expected, so I'm not going to take questions here and move on to this next part, and then I'll take questions between that step, that part of the talk, and the next one. Okay, so very recently we've been working on really pushing to a larger atom number and exploring what kinds of things we can learn from such a system. So how do we scale this system? What are the key challenges? So the key things that we care about are how clock-friendly our setup is, meaning how well we can drive the clock transition, and how scalable it is. So at 813 nanometers, which is the tweezer wavelength that we used for the work I was just describing, we use 813 nanometers because it's magic for the clock transition, where magic means that the intensity of the light does not change the energy of the transition, which is critical because if the transition moves around because your tweezer power fluctuates or because the atom moves around in that potential, then that spoils the coherence of the transition. So 813 nanometers is super clock friendly, but unfortunately it's not great for scaling. And the reason why is that the polarizability at 813 is actually pretty low. For instance, it's a factor of 3 lower than it is at 515 nanometers. The spot size is twice as large, and the power sources at 813 are not as good as they are at 515. At 515, the tweezers are very much not clock friendly. The transition is horribly shifted, but it's a very scalable system. So on the left here, I'm showing you recent pictures from our experiments where we can have arrays of 625 sites corresponding to above 300 atoms. So how do we combine these two things? So in this recent work, what we did was we have 515 tweezers, we have 813 tweezers, and we actually have one more additional potential, which is a lattice potential that helps us confine a bit more in the weaker dimension of our tweezers, which is this, what we call the axial dimension, which is up and down in this diagram. So this allows us to make pictures like these, where this is a single shot image on the left and then an averaged image on the right. I'll describe how we do this in just a second. These lattice, I just wanted to point out that having this lattice is actually a new capability for tweezer experiments, and it actually is quite useful. And we figured out a lot of cool techniques for actually making the plane of this lattice well referenced to the plane of the tweezers, and we can actually read out the phase of this tilt. So we can read out interferometrically this tilt on the atomic plane. That's what this is showing here. And we can make this phase line up with all of the sites. We can make this pancake line up with to be at a uniform phase with respect to the tweezer array. Sorry, that was a mouthful. Okay, so these images that I'm showing here are made by doing something where we load into the green tweezers, we do ground state cooling and detection there, and then we can actually load into the 813 tweezers and then load back into the green tweezers and do imaging again. So doing this basic approach, we can have very low loss transfer between the two potentials, and furthermore, we can do high fidelity ground state cooling green. That's the black. And then the gray here, where you can see we have a little bit of heating, that's the temperature that we have after we transfer to the 813 and then transfer back to the green again. So this gives us an upper bound on how much heating there is from this entire process, and further tells us what the temperature is when the atoms are in the 813 tweezers, which is what we really care about for clock spectroscopy. Importantly, when we have the atoms in those tweezers, in the 813 tweezer array rather, we can do high fidelity and narrow spectroscopy. So on the top here, I'm showing a subhertz feature with 150 atoms. So this is a 16 by 20 array, so we have 320 sites. And we can fit the individual centers of the spectroscopy and see that the distribution in traps is actually on the order of RMS, like 50 millihertz, which is about what we expect just from this magic frequency issue that I was describing in the middle part of the talk. So another key thing that we can do in these systems, which was, we didn't really know what to expect, is we can get to very long lifetimes. So the black data here corresponds to the ground state lifetime. We can get out to about 160 seconds as a function of trap depth. At lower trap depths, we start to see some loss. And then for triple P0, the excited state of the clock transition, we observe that there's a minimum. And so at these lower trap depths, this is just dominated by the loss that we see in the ground state case. And then at these higher values of the trap depth, where we start to see the lifetime get lower again, this is from spontaneous emission that we expect to occur. And this dashed gray line, this dashed black line, is the sum of our characterized loss plus the expectation of the spontaneous scattering that we expect from the tweezers. So importantly, at this minimum here, this corresponds to 50 seconds of usable interrogation time, which is actually a record for optical clock, neutral atom optical clock systems. And I want to sort of highlight why that is. So in the lattice clocks, there's this important problem. So I'm showing you a picture of a 3D lattice clock here on the left. And in this really important paper from Junyi's group, they showed that there's this maximum in the coherence time, which is set by two effects. So at deep traps, it gets better and better. And the reason why is because tunneling in the lattice gets suppressed more and more. But then on the left here, oh, sorry, I said that wrong. As you get to shallower and shallower traps, the scattering gets less and less from the lattice. But then on the right here, as you get to shallower and shallower traps, the coherence time gets worse because tunneling starts to occur. The thing that's amazing about tweezers is that you can control both the tweezer depth and their spacing independently, which means that you have control of the tunneling independent of the trap depth, which is not something that you have in an optical lattice. All right, so we really wanted to explore, given this kind of new capability for a neutral atom optical clock, what kind of coherence times we could get. And importantly, for doing these Ramsey experiments, now because we have 150 atoms, we could do single runs of the experiment, which means that we are not necessarily limited by averaging over the phase of the laser. And what I really mean by that will become clear in just a moment. So these are data from the experiment showing Ramsey plots. And these on the top right here correspond to individual snapshots from this long time scan data. Yes, and so these different shaded regions correspond to our measured atom laser dephasing. I'll define that in a moment. Our array dephasing, this is the non-magicness that I was describing a moment ago. And this light gray corresponds to the excited state decay. And so you can see that the variance in the data is pretty much dead on with the expectation of the array dephasing. So let's to understand really what's going on here, let's take these four snapshots that I have and sort of characterize them. Or maybe I should say not characterize, but categorize them. So on the left here, this corresponds to when we have atom laser coherence, which means that the atomic phase of the superposition is well defined with respect to the laser phase. And we have atom-atom coherence, which is to say that the atoms in the array have the same atomic superposition phase as other, like the different atoms in the array have a uniform superposition phase. At this point here, there's no atom laser phase. So there's a large variance in the distribution, but it's the fringe that we would expect to see as the phase of the laser changes is not apparent. So one way of thinking of this data is that we're just randomly averaging over a sine wave, but we're not actually seeing that sine wave because we're randomized over it. But because the atoms have relative coherence with each other, they can have large excursions within the expected Ramsey fringe that you would have if you still had atom laser coherence. And then finally, at 50 seconds, there is no atom laser coherence and there's no atom-atom coherence. The fact that we have single shot runs means that we can see this, because if we didn't have single shot runs, then at any given time, we would actually have to take statistics and average over the laser phase at a given time. The fact that we see these large excursions, another way of thinking about it is that the atoms are classically correlated. Even though the phase that they see with respect to the laser is uncertain on any given run, they're always pointing in the same direction. Because we have single site observables, we can actually probe this point. So this is a plot where I'm showing the nearest neighbor correlator. So looking at the end of the Ramsey experiment, whether the atoms on nearest sites are pointing in the same direction, as a function of Ramsey dark time. And we can see that on actually a 1/e time of about 40 seconds, this lasts for the entirety of this correlation, nearest neighbor correlation signal persists. And then at different times, we can look at actually a correlator map across the entire array. So this isn't just a nearest neighbor, this is between sites I and J, reference to the origin, at the center of this plot. And you can see that this signal gets weaker and weaker. And then actually in the middle of the, at about 25 seconds, the phase of the near, at distances that are larger actually flips sign. And the reason that this is happening along this diagonal, but not this diagonal, is because the frequency differences due to the different AOD frequencies is such that we expect exactly this effect. So this is actually a really cool verification of exactly this array dephasing phenomena that we expect to have. One other point that I'll highlight here is that there's this wave in our data that we actually don't totally understand. We're fairly certain it comes from a small inhomogeneity from tweezer to tweezer due to the way that we balance the sites, but we can't prove that. So it's just sort of an interesting feature of the data that we observed. Okay, so this data, I just really want to highlight the people involved here. So this is Aaron Young, Will Eckner, and then Nathan Shine, who was a new postdoc on this project, and together these guys have been total rock stars. All right, so I wanted to circle back to this point of what constitutes a clock, to point out that the quality factor that this system has, given that we know that this single atom superposition phase is actually well defined on a 30 to 40 second time scale, this corresponds to a quality factor of 10 to the 16, which is, to our knowledge, we're not aware of any other system that has seen such a large quality factor. I'm running a little bit low on time here, so I'm going to rush a little bit. So we have a way of, based on pioneering work in atom interferometers and the more recent work in optical clocks, to extract a stability from these measurements, even though we've lost phase coherence with our laser. I'm just going to sort of skip over that. I can answer questions if there are some. We can get to atomic stability. So this is the relative stability between one part of the array versus another part of the array, which are 5.2 times 10 to the minus 17. So this is basically on par with the state of the art in all optical atomic clocks. And we can get to a relative frequency uncertainty between two parts of the array at 4 times 10 to the minus 19. So this is the fractional frequency uncertainty. So the present conclusions from this tweezer clock system is that we can get to these really high quality factors that we can really observe. We can get to high atomic stabilities. One thing that's been really lacking in these systems and is on our agenda for next steps here is to do a full accuracy budget for these systems. We don't expect really to observe something much different from other, for instance, bosonic lattice clocks, but the is really in the point for this, and that's quite important for us going forward to do. The best performance that we think is possible for these clocks is to use strontium 87, for which there will need to be a bit of technological development to get there. And finally, as I'll talk about in a second, these systems are really an ideal test bed for studies of entanglement in enhanced metrology settings, where you're using entanglement to enhance the metrological signal. And by getting to these very long coherence times, what this suggests is that we could have, say, a 1 second long interrogation with tens of atoms. And I point this out just because really being able to use such a metrological enhancement is going to really depend on getting to very long coherence times, because once you add entanglement to the system, the many-body entanglement of that, or the many-body coherence of that system will decay even faster given your single particle coherence timescales. Okay. Maybe in the interest of time here, I'll take questions at the end and just rush through an outlook, because I think I have I'm at about 15 minutes here. So just quickly, the next things that we want to do here are really combine this long coherence time and interesting new Clark architecture with the fact that optical tweezers have been shown to be this great platform for generating well-controlled entanglement. And I also wanted to highlight here some work from the Andres group very recently, which showed in particular that in alkaline earths, you can get to very high fidelity Rydberg gates. So altogether, this suggests that you can combine these things to create long-lived, well-controlled, entangled optical clocks. Just to fly through these next couple of slides, a key challenge that we have here is that the fidelity of our clock rotations is not awesome, and we need to make that better. We know one of the main problems is from the finite temperature that we have, which is actually very low, it's 0.1, but the large Lamb-Dickey parameter that results from having these very shallow tweezers. And the way that we're solving that problem is by using an additional optical lattice in our setup that's referenced to our objective. And so just to quickly show this idea, so we can have our green tweezers and then load into this 813 tweezer. These are sort of horrible images, but actually what we were doing here was imaging in the lattice itself, which we don't need to do for the experiment that I'm describing right now. And we could do this with actually 75% transfer, so going from green tweezers into purely a lattice potential and then imaging there. If we took averaged images, we could see that the initial tweezer array and the final averaged image of the tweezers was actually pretty well matched. You can see this little ripple here that we actually think is because the tweezers weren't exactly aligned to the principal axes of the lattice. And we could do ground state cooling in this lattice. So this really suggests that we could get to much higher confinement and low temperatures in the lattice, which would take us to a much higher fidelity region of this contour plot. So this is, I should have said, this is a contour plot showing the fidelities that we could get to in the clock transition as a function of the temperature and Lamb-Dickey parameter, which is just a measure of the confinement, as I said. So our next steps, we want to add Rydberg excitation to this system. We so far have control, we have a home-built 1 watt UV laser system for doing Rydberg spectroscopy. We now have these 2D arrays, which will be very useful for getting a lot of entanglement in these systems, which is actually a very important point. You need to be able to have a large amount of connectivity in your system to get good metrological enhancement. We collaborated with the Zoller group to come up with this neat idea that uses ideas of VQE, variational quantum eigensolvers, to create systems that are optimized for squeezing. Finally, sorry to fly through these. I have a new project in my group that I'd be happy to talk about, and I might be looking for new people if you're interested, that's really focusing on reaching intermediate scale arrays where we have full local single and 2 qubit control. And then also I have a collaboration with Cindy Riegel's group to generate, create technology for trapping tweezer arrays or atom arrays in a cryogenic environment. Okay, with that, I'm gonna finish up here. So I hope I've convinced you that these tweezer clock systems and actually alkaline-earths in general and tweezers are an exciting new direction. I wanna highlight these guys here who did the majority of the work on the strontium experiment, as well as, and these guys down here on the new YB experiment. This is Alec, Jenkins, and Ioannis. Thank you for your time.
Thank you, Adam, for a really wonderful seminar. The chat is open for questions, so everybody should put questions into the chat. And okay, some people are clapping their hands in the chat, which is a good start. Yeah, okay, I hope some questions will pop up. While we're waiting, maybe, let's see, I have a few. But just to start with, so in the pictures you were showing of the 2D arrays, those are averaged? Or,
which ones?
I don't know, you have different ones. So I guess I'm wondering, do you have, in the clock, for example, were you randomly filling it?
Yeah, that's all of it. So this picture,
were you working with, and what was that? Yeah, okay.
So this picture, this was a picture of a single shot. And this is optimized to be like as fast as possible. So this is about I think it was a 20 millisecond image.
Okay, so the left is single shot and the right is
and the right is averaged, yeah.
50% filling roughly.
Yep, and there's no rearrangement here because we don't need to do that. But actually, we've just started doing that.
Okay, I want to get some questions from the audience. I'm not seeing.
I think there were. I saw 3 chats, but I don't know if there were.
So, let's see. We have lots of people in the audience, so they're just being shy, I think. Okay, well, while they're thinking, there's a lot of discussion always about sort of does squeezing help depending on what's limiting your clock performance. So I was wondering if you can say a little bit about kind of, what the current limitations are and whether squeezing will help now or whether you have to push on other things. And you mentioned the clock rotations, for example, the clock laser.
Yeah, so the clock rotations are key. So that will definitely be a limitation if we can't get the fidelities above 99%, but I think we can definitely do that with this lattice architecture. So for this variational scheme, we could show between 6 and 10 dB improvement. In a straight Ising model, the Pohl paper, which I think we've talked about before. That I think they got to about 3 to 5 dB, but best in a 3D lattice. And the reason why that matters, or why they needed to go to 3D, was because of this connectivity issue. So in an Ising model, the correlations that you get are only between those atoms that actually have a connection on your graph. The correlations do not propagate. So one interesting question, and which is one that's actually answered and sort of exploited in this variational scheme I was describing, is how much a transverse Ising model helps, because there you can have something that looks like hopping of your spin excitations that propagates the correlations in a way that can improve or can realize longer range squeezing and therefore larger entangled states. So I think there are actually just open questions about this that these systems are great for exploring. Two other points that I'll make regarding this question. So one, my personal view is that getting to these long coherence times is actually like super critical, because if you're always going to have to scale down your interrogation time because it decays, n times faster because you have more atoms, that's really going to hurt how well you can do, even at short-term stability. The second thing that's relevant is that strontium-88, which is this isotope we work with, I sort of swept this under the rug, but the way we interrogate the clock transition is by turning on a magnetic field. We have to do this because this clock transition actually is completely forbidden in this isotope, but adding this magnetic field mixes in a state which has a finite lifetime. What this means is that you might be able to do something where you turn on this field, induce coherence between up and down, and then turn off the magnetic field, which would mean that this coherence, this lifetime would in principle be infinite. So then you're not actually fundamentally limited by spontaneous emission. Of course, technical issues will still be relevant, but for long time scale interrogation of an entangled state, you're no longer limited by spontaneous emission, which could be a very cool strength.
That's a really interesting idea. There's a question that came up in the chat from Leo Holberg. I'm going to try to unmute Leo and let him ask his own question. Let's see what's this one. Leo?
Leo's a scary person to have to answer any question about clocks. Let me just tell that to the entire crowd right now.
Can you hear me?
I can hear you.
Okay. Very nice work. You're building up a ytterbium system. I'm curious as to what you see as advantages of ytterbium relative to strontium and or disadvantages in these.
Yeah, so definitely. Thanks for asking that. So a couple things. So the first is that doing high fidelity detection with strontium for quantum information is actually pretty hard. The reason why is that you can do it very well at 813 nanometers. I should say up front, my answer here is going to get in the weeds a bit, but I think it's sort of relevant for answering this question. So, so it's difficult to do high fidelity detection in a scalable large array at 813 nanometers. So if you want to get to say 400 traps, I think it's going to be pretty hard to do if you're doing the detection in 813 nanometers where the fidelity is much better. In ytterbium, it actually works very well to do high fidelity detection in 532 nanometer traps, which give you small point spread functions. So you have high intensity, which means you need less power per trap, and you can have decent polarizabilities. So that's one point. The second point is that you really want a good qubit that's not an optical transition. If you've rendered the problem of making a good qubit to one of using an optical transition coherently, you've basically made the problem of making a good qubit equivalent to making a good clock, which can be very hard, and especially if you need both to have long coherence times and high fidelity rotations. That means that you really want to work with a fermionic isotope where you can have a nuclear spin. The nuclear spin of strontium for the fermionic isotopes is very large. It's 9 halves, which corresponds to 10 states, which means that if you want to isolate a qubit, that can be very difficult. By contrast, ytterbium-171 is nuclear spin 1/2, which means you can have a spin 1/2 qubit in the nuclear spin. The second thing that the third thing I wanted to say about this is that for doing quantum information with alkaline earths, one thing that would be really nice is to be able to control this clock transition very quickly at high Rabi frequencies. And I think using a fermionic isotope is key for that, because using this magnetic field approach, it's pretty hard to get to Rabi frequencies above 5 kilohertz. Whereas using ytterbium, you could get up to, using a fermionic isotope and specifically using ytterbium, I think you could get up to Rabi frequencies of 200 to 500 kilohertz. So that's a bunch of technical reasons, but they're actually really important for making this kind of system work. Does that answer your question, Leo? I think you muted it.
So let's see. Leo, does that answer your question? Okay, well,
yes, yes,
yeah.
I agree. I think those are, I'm enthusiastic about ytterbium, but strontium also has nice cooling transition. So
yeah, I mean the lasers,
pluses and minuses.
Yeah, no, I think that's true. I mean the lasers are. We've just built this laser cooling system, and it definitely was a lot more annoying than it was for strontium, where basically everything is diode laser based.
Great. So we have a couple more questions in the chat. The next one is from Jason Hogan, and I'll just call on Jason. Jason, you're unmuted, so.
Oh, okay. Great. Yeah, I really like to talk. So I'm just wondering about this, the magic laser, the magic wavelength shifts that you see with AOD, and they seem to be, you're able to sort of account for them, I guess, by looking site by site. But are there any other issues that you see with those, maybe systematic errors that having site to site variation in the magic wavelength? Is there any reason to try to avoid having that in the future with how you trap?
This is a great question. I think the short answer is that yes, we want to avoid doing that. And actually, this is one of the reasons why we are setting up this SLM, because then we can make arrays that are all at the same optical frequency, and we no longer need to care about this. Manuel's group actually had this really clever idea for getting around this, where they work at a particular depth that allows you to be quadratically insensitive to some of these shifts. But I think the really optimal thing that you'd want to do here is just to get rid of them entirely. And so that's what we'll do. I should point out that the nearest neighbor correlator measurement that I was showing, that's actually not limited by this problem, because there the frequency differences are so small. That's the sort of the virtue of using the nearest neighbor correlator. I'm not positive I actually said that, but I meant to say it. But you can see, of course, for longer range correlators that this frequency difference does become important. Does that answer your question?
He's muted. I'm trying to unmute him. Let's see. Jason?
Okay, there. Now I'm unmuted. Yeah, that's great. That's what I was wondering. Very interesting. Thank you.
Great. So we have one more question that's from Shankri Rajagopal. Shankri, I think you're unmuted now, and you can ask your own question.
Great. Thanks. Thanks for the talk. I was wondering whether you need anything sort of special beyond wave plates to control the polarization of such tightly focused tweezers, or if that's like a second order effect compared to the AOD shift for maintaining the magic wavelength condition.
So this is an excellent question. And there's it's sort of a two-part answer. So which part do I want to start with? Okay, I think that's more logical. All right, so the first part is, so strontium-88 is spin 0, which means that actually the polarization at the focus does not matter. You only have the scalar shift. Now, this is very important, in particular in the context of tweezers, because there's this key effect where at the focus of the tweezer, because you've confined the light to a volume that's on the order of the wavelength, you have the electric field of the light bends around the focus and actually gives you polarization inhomogeneity. On one side of the tweezer displaced to, say, the left, you have circular polarization with one helicity, and then to the other side, you have the opposite helicity. This means that if the atom is not cooled well, it could average over these polarizations. Now, the second part of the answer to your question is that while this does not matter for strontium-88, if you wanted to have a clock that had the best accuracy possible, you're probably going to want to use strontium-87. And if you're using strontium-87, these different polarizations might begin to matter because you have a nuclear spin in the ground state and the excited state. So the answer to your question is, it didn't matter too much for what we were doing right now, but it definitely could matter if we were trying to do a very high accuracy measurement in strontium-87. Still have people here? Okay, sorry, yeah.
Oh, was someone else speaking?
Oh,
No.
I thought I heard something, but I'm not sure.
I did too. Okay. I don't hear it anymore. So, but I think that was a very clear answer. And I think are out of time, but this was a really fantastic seminar. So thank you again. And I actually have lots more detailed questions that I'll bother you with offline. So let's thank Adam again for a great seminar.
Thanks so much for the invitation. Bye all.